Hello everyone. Today I'm going to be talking about the top-level physics requirements and simulated performance of the MRSt. MRSt is a spectrometer for time-resolved measurements of the neutron spectra of ICF implosions. The MRSt is based on the combination of the principles of the MRS, the Magnetic Recoil Spectrometer, which is currently fielded on the NIF, and the pulse dilation drift tube concept. This poster is going to present the top-level requirements for this diagnostic, as determined by simulations. First, I'd like to acknowledge my collaborators. This is a collaborative effort between MIT, the University of Notre Dame, and Lawrence Livermore, and has been supported by the NNSA through our Center of Excellence. So as a general overview, from the MRSt measured time-resolved neutron spectrum, the time-resolved values of the ion temperature, the areal density, and the neutron yield of an implosion will be inferred. These implosion parameters will then be used to probe the impact of alpha heating and various failure modes like P2 asymmetry and mix. Hydro-simulated values of ion temperature, areal density, and neutron yield, resolved in time, were used to define the top-level physics requirements for the MRSt. Monte-Carlo simulations were then used to determine whether the system can meet those requirements. Shown here for reference is the ion temperature, neutron yield, and ρr of a particular simulated ignited implosion. This is the kind of thing that MRSt is going to measure. So first of all, numerous simulations were used to determine what the top-level physics requirements of MRSt should be. These simulations were performed to study the impact of mix, P2 asymmetry, and alpha heating on the ion temperature, ρr, and neutron yield as functions of time. We then determined the requirements shown here in this table on the basis of the sensitivities to these parameters. So, shown here is a few of the simulations that were performed in this ensemble, where the yield enhancement due to alpha heating was varied, and as you can see, the derivative of the ion temperature with respect to time at bang time and the derivative of ρr at bang time both vary as the effect of alpha heating changes. And so, in order to ensure that we can probe alpha heating as well as the mix and P2 asymmetry of an implosion, it was found through these simulations that we will need these required accuracies for each of these parameters that we want to measure. Each of these represents a 1 sigma accuracy that we want to achieve with the MRSt. MRSt will be configured in 3 modes on the NIF target chamber, depending on anticipated yield. So here is a depiction of the NIF target bay with MRSt mounted on it, and there are 3 different configurations that we examined in this study, each of which has a different resolution and efficiency. So there's a high efficiency configuration, which has a thicker foil, a larger foil, and also a wider aperture to obtain higher efficiency but worse resolution. A medium efficiency mode, which is a smaller foil and a smaller aperture, and then a low efficiency mode, which is the smallest aperture and foil, and which achieves the best resolution. These 3 configurations were each examined in comparison to the physics requirements that we determined, and in addition, it should be noted that the CD foil that produces the recoil deuterons that the MRSt measures can be replaced with a CH foil to get protons instead of deuterons, which yields 2 times better time resolution. So next, Monte-Carlo simulations were used to predict and evaluate the MRSt performance. So from the simulated ion temperature, ρr, and yield, a time-resolved neutron spectrum was constructed with a simple analytical model. This spectrum was folded with the response function of a particular configuration of the MRSt, and from there, synthetic data were generated with Monte-Carlo techniques from which a time-resolved neutron spectrum was inferred and used to infer implosion parameters. We then took those inferred implosion parameters and compared them to the values based on the original simulations to get an idea of the accuracy of these configurations of the MRSt. These accuracies can then be compared to the top-level physics requirements that were determined by the ensemble simulation. So shown here are some examples of what these calculations look like. These are three important implosion parameters: the burn width, the burn skewness, and the ion temperature derivative at bang time. And as we vary the yield of the simulated implosions and thus the statistics in them, we see that the accuracy of these inferred implosion parameter measurements, represented by the blue dots, gets better as they get closer together and converge at the orange line, which represents the correct value that they converge to at high yields. And then the shaded orange regions represent the previously shown physics requirements. So we want the blue dots to lie primarily within the orange region. And you can see that at current NIF yields, roughly in the middle of the x-axis, we do generally get that. We have the majority of the blue points inside the red regions, which indicates that these requirements will be met at those yields. So to conclude, here is shown all of the requirements that were calculated with the hydro simulations, as well as the estimated accuracies of the different MRSt configurations at certain yields. And you can see that most of the top-level physics requirements are being met at these yields. So according to these simulations, the MRSt will meet most of the requirements at current NIF yields. And at these yield levels, the MRSt will provide valuable information on mix, P2 asymmetry, and alpha heating. And that concludes my poster presentation. Thank you.